Hello and welcome. Thank you all so much for joining us today. We're really thrilled to see so many attendees. We have 176 registered. So that's pretty impressive and a new record for the SCTE. So thank you all very much. Welcome to High Capacity, Lower Power, achieved both with DGA. This will be presented by Jan Ariesen, CTO of Technetix, who most of you should know. And if you don't, you'll learn to know him today. It's not often I find myself wearing both hats, but today I've got the Technetix and the SCTE hat on. So here, I'm really impressed to see so many people I know from the industry online tuning in these really strange times. We've got participants from 27 countries. So China, the USA, Netherlands, Kenya, Australia, Croatia, the UK, of course. But it's a pleasure to welcome you. And if I've forgot anyone, really sorry. Distributed gain architecture. This is going to change the face of our industry. At a time when technology has never moved faster, consumers have never been more ready to adapt to change. It's an exciting time for the sector. DGA is the network equivalent of the iPhone hitting the market when most of us were still relying on the Nokia 3210. It's a little short of revolutionary. And in the next hour, we're going to hear all about how this technology will impact our lives for the better. This is our second webinar, and we've been delighted with the response so far. Helping Technetix also reach their audience to broadcast an industry development with seismic simply reinforces for me the role that the SCTE has and plays as an agnostic champion of knowledge and education. For 76 years, the SCTE has been a champion of such learning. We have a lifetime of standards training experience all at our fingertips, and our board memberships, relationships with some of the best in the business. I'm going to stop talking now and hand over to James, SCTE Executive Member and Learning Experience Manager at Virgin Media. He's going to be posing the questions and controlling this webinar. James, it's all yours.
Thanks, Tony. Controlling sounds like a dangerous word, so moderating is much better. So just a quick introduction for the kind of setup and the agenda for today before I hand over to Jan. We're shortly going to go kind of into a presentation / demonstration. To get the most out of this, just a quick recommendation around kind of Zoom and the best view for you to see this. If you're accessing via a desktop or mobile device, you should find there's a view button. On a desktop, it's normally in the top right corner. To get the best experience for this, if you just swap yourself into what you can see there as speaker view, just means you'll be able to keep the speaker on the center of the screen at all moments. So before I hand into Jan, presentation is going to last around 45 minutes. We're going to leave a little bit of space at the end for kind of Q&A. We're also going to flip the format a little bit on its head, and Jan's going to be inviting questions live throughout the presentation. So my job's going to be to kind of get these, collect them together, and I'll be firing these over to Jan as we go through the presentation rather than waiting for the end. We've already had some great questions submitted. So we've already got those and got them primed roughly for where they'll lie in the presentation. But for anyone, as we go through this, if you do think of a question that you want to raise or ask, then a couple of options you can do. There's both the chat and the Q&A function in Zoom. So just pop your question in there. With the Q&A function as well, you've got the option to kind of ask anonymously. What we'll do is behind the scenes is kind of sift through those questions and we'll pose them to Jan at the right moment in the presentation. So that's pretty much it from me now. I'm going to hand over to Jan shortly. For those that don't know Jan, however, just a bit of an introduction before I do hand in. So Jan's been in our industry since 1983 when he joined TradeTech Telecom in the Netherlands. It was here he developed numerous head-end access network and in-home products. TradeTech and Technetix then joined forces in January 2005, and then Jan's role expanded. He became more involved in the technology and commercial teams and was appointed CTO, Chief Technology Officer, in 2012. Since then, with his team, he has created innovative technologies and products that improve customers' network performance while driving down the total cost of ownership. In 2020, Jan also assumed responsibility for research and development and product line management, and now sits on the Technetix board. Jan's focus is on liaising with customers to establish their needs and to be Technetix technology advocate, developing new technologies and product platforms with the customer in mind. He is passionate about learning and regularly conducts training for customers and key industry bodies, in addition to conducting regular training sessions for the team at Technetix through the Technetix Academy. All of which leads me to conclude that the presentation you're about to watch is entirely in keeping with this ethos, and his passion for training has led to the development of the Technetix studio, no less, where he is now, like a coiled spring, ready to impart his knowledge. Jan, over to you. Oh, I'm mute, I think.
Yes.
That's better.
Thank you, James, and thank you, SCTE, for the opportunity to demonstrate to you where we are working on. And one of the technologies that we are working on is the distributed gain architecture, DGA. What I want to show you in this presentation is what is distributed gain architecture and why do we do distributed gain architecture. We also want to show you a network built where we have the taps, the DNA amplifiers, etc., built into a DGA network, followed by a live demo where we are demonstrating the technology, demonstrating the signals, etc., that goes through such a network, and then we close down with the financials and the conclusions and the Q&A. As James said, if you have any questions, then please ask. So first of all, what is DGA? DGA, the idea of a DGA comes from the amplifiers, where we normally have a coax, and what we want to do, we want to transmit signals over that coax. But because we lose signal levels on it, we have to put amplifiers in to boost that amplifier to be able to reach a longer distance. As you can see here, we have a signal that is boosted in this amplifier. We lose this again on the coax, then we put an amplifier, etc., etc. And that way we can transport signals on a longer distance over coax. DGA is the same, but only now we do this on a shorter distance. So we have the same coax, but now we distribute with small amplifiers, we distribute the signals on the coax. And if you now look to the levels, you can see we have less gain because we have to overcome shorter coax. So we have less gain here, we boost it again, etc. So now you see we have the same approach in DGA as in normal amplifiers, only we are spreading the gain over multiple sections. And if you look to it, what that comes from is that if you look to a big amplifier like this, an amplifier consists of 3 stages, where you have a pre-stage, you have your driver, and you have a hybrid. Sometimes, even with the high power, sometimes you even have 2 drivers. So then you have 4 stages inside. So what we do with DGA, instead of having them combined in one solution, in fact, we are coupling the pre-stage and the drivers into the network. But as you can see, we are skipping the hybrids. We don't use those hybrids anymore in this design because we don't move them to that line here. And if we can remove the hybrids out of an amplifier, that will give us a lot of benefits. And I want to show you what type of benefits that are. I want to look to a number of things. So first of all, I want to show you the reliability. The reliability of a network is calculated with the so-called MTBF, mean times between failures. What this means is that, for instance, you are calculating the performance of an amplifier, how reliable it is, and that has a total result of maybe 100,000 hours. Then you can say this amplifier or this device will work 100,000 hours without any issues. And maybe it will do 200 or 300 or 400,000. But that 100,000, that is what we have calculated that this should work at least without any issues. That is the way how we calculate the MTBF. And if you now look to an amplifier like here, where you have 3 or 4 stages, when you look to a high power amplifier, the MTBF of such an amplifier is about 75,000 hours. That's about 9 years. So this amplifier should work for about 9 years without any issues. But according to the rules, we now have 3 amplifiers like this. So we have 3 times that 9 years. So statistic, you can say that the lifetime of this signal system is at least 3 years. So we divide that 9 years by 3, so we have at least a reliable network for at least 3 years. That's how we calculate the MTBF of a network. We also do this for DGA. But as I said, what we don't do for DGA is we don't use hybrids. And hybrids are by far the most power-consuming component inside an amplifier. And if you have an amplifier, a network and a line extender, for instance, roughly this size, the hybrid is about 2 centimeters wide by 0.5 centimeter. And all the power goes in that small component. And you can see here, there are about 50 different components inside one hybrid. And all of those components are in one small location, and that will consume for high power amps close to 20 watts. So 20 watts is only in that small device, and that will bring stress into a product. Of course, we are using this for a long time, but what we don't want to use this anymore going forward in the DGA approach, because now we can use only mimics. And if we go from hybrids to mimics, you can say that the reliability improves a lot. Because now we have that mimic is already used for a long, long time, extremely robust component, and we don't have that stress anymore. So now we have with an amplifier for DGA, it's easily 1 million hours. And if you divide that in this network here, now we divide this of course by 6, because we have 6 of those small amplifiers. You see that the MTBF is about 19 years. So even with double the amplifiers, the MTBF is still more than 6 times better. So the reliability of my network improves a lot. That is what we talk about reliable networks. So going forward from big amplifier to small amplifiers, one of the plans is that the reliability of the network gets better, because the network connection has to be much better nowadays, because nowadays we have internet, we have telephony, we have all the signals going over the coax. There's a lifeline, and it has to be up and running. We don't want amplifiers to go down or etc. So we want our network to be as reliable as possible. And this way of building it, we are de-stressing the network and we get a much more reliable network. That's about reliability.
Yeah, and a bit of a question that probably a right time to pick this one up actually. Just seeing this and obviously the move to more active equipment. One of the comments we kind of fed in before was just around the industry seems to be moving towards the N+0 type model and less actives in the network. Not necessarily a question, but just whether you've got a response for how this stacks up compared to that.
Yeah, no, it is true. Also for us, it says, okay, we go from this case from an N+3 to an N+6 network. So we're going to put more actives in the network. But as you can see, we have less active stages, because here we have 9 stages, while here we have 6. So what we are doing, we are still lowering the number of amplifier stages in the network, but we're also distributing them over the network. And that will give you the benefit. So I agree that it sounds strange to go from an N+3 to an N+6 network, but if you go from 9 to 6 stages. And overall, there you can see also in this calculation that the reliability of this network gets so much better, because now you have everything grouped on one location. And there's a lot of stress in that one product to put everything there. I'll give you an example. I will come back to this later, but the power consumption of such an amplifier will be about 35 watts. So the unit gets really warm and all these kind of things. The power consumption of such a small amplifier is about 6 watts. So you can see the huge difference in the power consumption, and therefore it generates much less heat. Less heat means less stress. That's why you have a better, more reliable network. So yeah, I understand the worries. I understand that you say, I go from N+3 to N+6, but you can say, I go from 9 stages to 6 stages.
And one more before we move on from mean time between failure. Let me get my words out. Just literally coming through it on the chat. So I'm just going to read it out ad lib. If the hybrid MTBF is 75,000 hours, surely the reliability is higher at 3 years than 9 years. So the assumption that the mean time between failure reduces from 9 years to 3 may not be logical.
No, but that's how we calculate MTBF. There's the rules of MTBF. There is a standardized rule you can find on the internet. And if you have, for instance, you have one component that is 10 years and you have another component of 10 years MTBF, then according to the rules, you say the combined mean time between failure is 5 years, because they both have 10 years, and then statistics view of that is then that the lifetime goes to 5 years. But that's the same as what we do here. Also here, it makes no sense to divide this by 6, because we have 6 times that 1 million, at least 1 million hours. But I want to compare apples for apples. I have more amplifiers, so you have twice as much amplifiers than I have in here. So that's why I want to play honest here. That's why I divide this by 3 and I divide this by 6. But it is true, I understand, but that's how we calculate it. And it is not that the MTBF of the hybrid is 75,000 hours. The MTBF of the complete units is 75 hours, because it's the hybrid, it's the power supply, it is all the other components inside this product that sets a mean time between failure. Because the hybrid, of course, is much more reliable than 75,000 hours. But it is one of the products that you will see in an amplifier that has the most stress due to all the power consumption.
Cool. And I've literally had one more come in, so sorry, hold you on this one, but then we're going to move forward, I promise.
No.
So just talk through why the third stage of the amplifier is no longer required. Obviously, you've kind of shown on your previous one that the third stage is gone.
Yeah,
why is it no longer necessary?
We'll come back to that later, James. I have some slides about that. I understand that. It is that's why we have less gain. If we talk about the product here, we talk about 44 dB gain, while here we talk about 20 dB gain. And because we have less gain, we have a shorter distance, we don't have to go that high in the level, and that's why we don't need the hybrids. The hybrids are the final amplifier to boost the signal a couple of dBs up. And we don't have to do this now, because we don't have to go that high level, because we don't have to overcome that long distance. But I will show you that later on in the slide.
Awesome.
Okay. The other part I want to talk about is the signal level and signal quality. And I'm sorry for a little bit of theory about amplifiers, but I want to explain to you how an amplifier works and how amplifier works in a cascade to understand why we believe DGA is such a good idea. So if you look to an amplifier will, as we said, will gain the signal. So let's say on the input we have a signal A, we have a gain in the amplifier G, that comes out of that amplifier will be A plus G, and that will be the gain. So the input signal plus the gain, that will come out of that amplifier. But unfortunately, amplifier is not ideal. So there are more things coming out of this amplifier, and we call that noise, we call that second order, third order, fourth order, etc. All these components come out of this amplifier. Intermodulation all comes from the signal A, and noise is what an amplifier generates himself. If we put an amplifier in a network, let's say that we have a second amplifier over there, we have a coax in the middle, and let's say that the loss of the coax is L. Then what goes into this next amplifier then is A plus G minus the loss. That will be the input signal of that amplifier over there. And that's, again, the same for the noise and the intermodulation and so on, coming out of this amplifier. So this is the input signal here. And that amplifier then has also a gain called G. And now what comes out of this amplifier is A plus G minus L, my input signal, plus the gain of this product. The way how we align networks, we call it unity gain. That means that the signal coming out of here is the same as the signal level coming out of here. So in fact, you can say that the gain here compensates the loss. And that's why you can say that that is 0. So what comes out of it again is A plus G, same as what we have coming out of here. But we have again the noise, this noise coming out of it, noise and intermodulation. But we also have the noise and intermodulation of the second amplifier coming out of it. So all of these signals come out of this amplifier. And the way how this adds up is that there is no relation in noise. The noise of this product is independent from the noise of this product. So because it's completely different, you add up with 10 log. You can say that noise always adds up with 10 log. So if my noise of this one plus the noise of this one is 3 dB more, because it's 10 log 2 is 3 dB. Intermodulation is different. Intermodulation all relates to the signal A. And that is in this situation, and that is in this situation. It's not that it is 100% the same. Because if it's 100% the same, it would add up with 20 log. But it's also not completely different. So it's also not 10 log. So at Technetix, we always use the rule that intermodulation adds up with 15 log. So all of this adds up with 15 log. And the reason why this is important is in a cascade. Because now when you look to the same cascade here, then if you look to the signals, you can say that the higher the TCP, then normally the quality goes up because you get further away from the noise till a certain moment, and then intermodulation kicks in, and then the quality drops again. And then what we normally do, we align the amplifier to be the best possible performance, that we get the best possible quality out of that amplifier. And we call that the TCP. As we just said, inside such a unit, we have a hybrid. And let's say that the hybrid has a TCP of 72 dBmV. That means that on the output of the amplifier, we have 69, because we lose about 3 dB in diplex filters, test points, power couplers, etc. So between the hybrid and the output port of the amplifier, we lose 2.5 to 3 dB. So let's say we have 69 dBmV as the best possible amplifier location for this amplifier. That also counts for the second one. So now we have 2 times, this one has 69 and this one has 69. But what we just saw in our previous slide is that noise adds up different than intermodulation. And that's why the combined performance of this link, you can see this one adds up with 10 log, but this one adds up with 15 log. So you can see that in fact, the ideal working point is moving backwards. So now it's moving to the left, because if I both align them on 69, then this is my cascade quality. If I would have aligned this, as an example, on 76 or 67, this would be my quality. So you can see my quality increase if I both give them a backup about 2 dB. And that is because, as I just said, intermodulation adds up different than noise. And that's why in a cascade, you cannot just combine amplifiers. And you cannot say, oh, this hybrid can do 72 dBmV, so I drive all amplifiers on 72 dBmV. Because you can see if I am on 72 dBmV, my quality ends up somewhere around here. That's how quickly this goes. And that's important to see this in a cascade. Because now we have 2 amplifiers and we have a number of taps. And if we drive a signal through here and we look to this amplifier here, let's say this is the output signal. The 2 things that is always important for an amplifier, as we discussed, is noise and intermodulation. Those 2 things are absolutely the most important parameter around an amplifier. If we then deliver signals, let's say we have 1.8, 1.2, and 862 megahertz, those are the levels we need to transmit out of this amplifier to come close to that amplifier over there. So these are the levels I have on my first amplifier, and that level will go through my network to my first tap, second tap, third tap, etc., till I reach the next amplifier. And now you see that although I put 1.8 gigahertz very much in the intermodulation, I'm still drowning in noise on my next amplifier, because I'm going to lose about 15 dB more in my network on 1.8 versus 1.2. And that's a huge extra loss. So you can see that that signal is decreasing. And now this is my input signal here. I gain this again, so I have my next line. So this is how the network performs. But if I now look to the quality, if this is my starting quality here, then that starting quality, this is the quality of this first part. And then this is, of course, now my starting quality of my second amplifier. So this is the quality of the second part. So this is how the quality of my network performs. If I do the same for DGA, then I have smaller amplifiers with taps in between. I have the same idea, look to the amplifier, output levels, and we have intermodulation and noise. But as you can see, now I don't need to drive this anymore into the intermodulation because the distance is much shorter. I don't need those extra levels. So now I have 1.8, 1.2, and 862. And if I now look to the levels over here, and I go to the first tap, the second tap, the third tap, and then I come to the amplifier and I gain again. And now you can see this is how this performs over the network. And as you can see in here, I don't enter into the intermodulation and I also don't come into the noise. So I try to stay away from the area where a network will have issues or the signal will have issues. And if I now do the same with the quality, So I have my quality here, starting point. Then this is how the quality now performs over this network. And if you compare that, the quality, this is the DGA solution, the blue line, while the black line is the high power amps. So with the high power amps, you can see it was not only that I was struggling with the levels because I was drowning in noise here. So the customers connected to the taps here don't have enough signal, but also the quality is reduced a lot. And those two problems will cause that you cannot transmit anymore 4K QAM, 2K QAM, 1K QAM. Maybe even have to go back to 64 QAM or all the way down, because you have to step back in your quality because your level and your quality is simply not good enough anymore. That is about the quality part. And the last part I want to talk about is power consumption. I already discussed that briefly.
Sorry, quick question.
Sorry?
Just popped up. Quick question, probably the right moment, just before we wrap up the last little bit. Is there an upper limit to the frequency? So you spoke about 1.8 gig up there. Would it go past that? What's the...
No, the higher the frequency, the more convincing DGA becomes. Do I say that correctly? I hope my English was good enough here. I will show this here. If I want to go to a higher frequency, so I even go to, for instance, I have this graph here. And you want to go even higher, let's say 3 gig, then this line has to go even higher to overcome this distance. And you can see it's impossible because the intermodulation will be so bad that the quality will just drop. It will absolutely be impossible to transmit that on that part. But if you go to DGA, and now I look to the same idea here, where I have the signals. Now you can see, even when I go to 3 gigahertz, yeah, maybe I end up here a little bit. So maybe I have to go then to two taps between the amplifiers. But that solution will work. This solution absolutely works, DGA, even in a 3 gigahertz network. But DGA in a 3 gigahertz network is a must. It's impossible to do that on a different way than DGA. So 1.8, you can still think about, okay, I go for a special tilt with zigzag tilt or lightning bolt tilt or things like that. But at the end, you are only sacrificing the quality. You are sacrificing the quality that you can deliver to the customers. So you have to go back to a lower modulation scheme. And that's not why you go to higher frequencies. The drive that every operator has is that we want to achieve that 10 gigabit goal. And if we have to switch back to modulation schemes and we cannot put enough bits anymore in 1 hertz, at the end we result that we are building a network, but we're already compromising the quality from the start. And it's not needed, because with DGA, is not needed. So yes, we can go to higher frequencies, but if you go to higher frequencies, DGA absolutely is a must.
Thank you.
Power consumption. Power consumption, this is how an amplifier works. So you have a certain output power that an amplifier can deliver, and that's fine till a certain moment, and then you have to increase the power into the chip to be able to deliver the additional power. So here you can see that, for instance, you go from 1 watt to 3 watts to 6 watts and to 18 watts to 35 watts. So every time you have to increase the power consumption in an amplifier module if you want to deliver bigger signals. So if I look to a DGA network is roughly around here. So you can see we can build DGA networks with an amplifier about 6 watts. If you go to a DBX, our normal modular platform, we are roughly here on our total composite power, what we can deliver. And what we talk about at the moment, to go to 1.8 gigahertz, said, yeah, we go for double power consumption, we have more level. At the end, what you have, this is where you end up. So you end up with a 3 dB more signal output power, but you go from 18 to 35 watts power consumption. So that's what we call with high power amps, because we have to increase the power inside the device so much to achieve that few dB extra, that here with the DNA, we only have 6 watts, while here we talk about 35 watts. And if you put this in a network, as we just discussed, we have the 3 amplifiers here. Now we have 3 times 35 watts. So that's 105 watts. And we have 6 times 6 watts. So that's 36 watts. That's the difference you have in power consumption in your network if you go for the high power solution or you go for the DGA solution. And if you compare that, for instance, with a city of 500,000 homes passed, then you need about 20,000 of these amplifiers, or you need 40,000 of these amplifiers to feed the signal through 500,000 homes passed. And to do this, then for the power cost, if the cost is, let's say, 10 cents per kilowatt hour, then this will cost you $613,000 to power this network for 500,000 homes passed. And if you go for DGA, it will cost you 210. So this is $400,000 different to power this network or this network. So we just talked about a lot about that we have better quality, that we have more reliability, etc. But also financial. This is a much better solution because, as I said, that few to be extra to get out of here, I go already from 18 to 35 watts. That's the big difference. But that's what you need to have a traditional locations, so the amplifiers like we have here, to go to 1.8 gigahertz. So what we believe with DGA, what you get is more for less. You're going to get more quality. Because we have more quality, we also have more data capacity. We can deliver, we can put a higher modulation scheme, more bits in the hertz. We have better levels. We can meet all the requirements for DOCSIS 4. That's all possible to do this with DGA. And we have more reliability, as you could see in the calculations. We have less power. Shares less power. It's about 30% of the power consumption of a normal network. That's how big that difference is. So you can save yourself 2/3 on your power bill to go to DGA versus high power amps. So what is this, how is it going to build? Any questions so far, James, on this part before I move on? No? Okay, then I move on.
So yeah, I've got a few for this one, so I'll let you do this slide and then I've parked a few ready for this one.
Okay, great. So we built an amplifier to do DGA. It's a small amplifier, although it's a big picture, but the size of a tap, an outdoor tap, input, output, and this is a small amplifier to do DGA. This is an amplifier that don't have the hybrid, is using only the mimics. This amplifier, the MTBF of this product is 1.5 million hours. That's how big, how reliable such a product is. The power consumption of this product is below 6 watts. And if you look to the frequency response, you can see here, we start at 54 and we go all the way up to 1.8. And the upstream starts at 5 and goes all the way to 684. And as you can see in this area here, we have gain in both directions. We have gain down and we have gain in the upstream at the same time on the same frequency. Because if we go to DGA and we only have that 20 dB gain block to have DGA, we can build this without diplex filters. That means, and if you have no diplex filters, then suddenly there are a lot of more opportunities because therefore we have no guard band. So now if you have 204, as I say, we go for a high split, you have 204, 258, that means that 54 megahertz is gone. That frequency you have to throw away. If you go to a higher frequency, that even becomes bigger. According to the cable labs, it says if we go to 684, the guard band is 180 megahertz. So you have to throw away 180 very good usable frequency capacity. You have to throw it away just for your guard band because you have no filters. Now you can say, I stop at 204 with my upstream, so my downstream can start at 204 because I have no filters anymore. If I go to 300, I stop at 300 and my downstream starts at 300. And that's why we even can do flexi split. We can say I put my split on 200 megahertz. I need more upstream, I go to 300. I need more downstream, I go to 100. I can constantly move them around because I have no filters anymore. So I can just move around where I want to put the split. And I have no guard band. So now I can just glue them together. But because we have no filters, we also can do full duplex. We can do frequency division duplex. All these things are possible because we have no guard bands anymore in our amplifiers. So everything that goes down gets gain down, and everything that comes up gets gain up. And that's doable because now we talk about small amplifier devices, and we can build this inside this device in a small device where we have that 20 dB gain on 1.8 gigahertz. You had questions, James?
I do. First one's around the guard band, actually. So you've just spoke about you're not needing the guard band with kind of your DGA. Is there any reliance on the equipment around it? Does the rest of the network have to play the same kind of, or can you work this in an existing network?
I will go to the next slide. That's maybe the easiest. So if we have DGA, so we have a DGA network here. We have a remote PHY or remote MAC-PHY here. We have a CPE device there. And where you put the split is all down to the CPE and to the remote PHY or MAC-PHY. So in fact, because we have no filters anymore, you can say we have one big transparent pipe. And so we don't rely on filters anymore. And that means that it's all down to the software, where the software tells the RPD where to put the split. And that's the beauty of it. In fact, what we do, we go from a hardware-defined network where we had filters and we said, okay, this is where the upstream is, this is where the software is. We now go to a software-defined network because the software can tell me where to put the split. And I can change this on the fly. I can constantly move this around because it doesn't matter anymore. It's now completely controlled by the software. So no, there are no additional parts. Every CPE device should be able to have that according DOCSIS 4 should be full duplex ready, so can be up and down mixed to each other, and that's the same with the RPD device.
Cool. This one's just on output level. So the DGA device is shown on the previous slide. What's the typical output level?
Yeah, so normally what we are aiming for is a TCP somewhere between 55 and 60 dBmV. Cool.
I think that's all for this moment. I'll let you carry on.
Okay, great. Now what we want to show you, this was the theoretically story about DGA, but how does a DGA network really looks like? And we want to show you that we built a DGA network on the wall. So please stay with us for the 10 seconds when we move the camera around so I can be on the other position and I can show you how that network looks like. Okay, welcome back. So this is our demonstration wall. So what we built on this wall is in fact 3 networks. I want to talk you through all the 3 of the networks and then focus more on the DGA approach. All those 3 networks are our solutions for DOCSIS 4. We're talking about ESD or FDX solutions. Now the first one we have on top is our normal DBX platform. It's a modular platform that can be an amplifier, a node, or a remote PHY, or next year even a remote MAC-PHY. Then this product, as an example, will turn over. This is now a remote PHY device with the pebble inside from Harmonic, where we have the input signals turned over into digital signals into RF. That RF signal is now transmitted and we need to go to the next amplifier. If we want to go to higher frequencies and we are struggling to reach the next amplifier, and we saw that in my demonstrations before, then what we can do is put also this DNA here as a booster amplifier. So now we gain this signal with about 20 dB. So we don't want to put an additional 3 dB here and double the power consumption. No, now we only add 6 watts and we add 20 dB to the signal. So you can see we have a much better signal going through. This way, we come now to our plugin. This is the module that we can fit inside in a Cisco gain maker. So you can remove the Cisco gain maker and you put this one in, and then we can go to 1.2 or even to 1.8 gigahertz. It's completely digital controlled. So from here, we can control this from a distance, levels, etc. So with a DOCSIS modem, etc. But from here now, we distribute the signal again over the network. So here you can see we can distribute all the signals up to 1.8 gigahertz. All of that signal will go through here, And then here we have our taps, our 1.8 gigahertz taps, our DNA amplifier, and then we go to the next one. So in the moment that the signal gets too low, we put the DNA in as a booster amplifier. We do the same in this situation here, but that's more an European cabinet style solution. And this time we work with the Vecima remote PHY device. Same story, we turn over the RF to the digital to RF. We want to reach the next amplifier, and we use the DNA as a booster to make it to the next part. This is two solutions that is somewhere between the high power amps and the DGA, because it's already the first step to DGA, because we are using the DGA amplifiers, but in this case, we are using them as a booster in a normal network. The middle, this is our DGA network. So now we have an input signal here, and the first thing we have here is a lossless splitter. And a lossless splitter is the same as a DNA amplifier, only it has one input and it has 3 output ports. So you have one input and you have 3 times the output, but the insertion loss from in to out is 0 dB. And that is from in to out to this one, in to out to this one, in to out to this one. So we split in 3 directions with 0 dB loss, and that's on the upstream and the downstream. Same idea with the DNA amplifier, where we have no diplex filters. Also here, we have no diplex filters, but now we combine an amplifier with a 3-way splitter. Then we have 3 lines leaving. So we have one line, let's say, that goes to our taps here. We have one other line that goes to the DNA amplifier. Then from the DNA amplifier, we boost the signal with 20 dB, as we saw in the previous picture. Then we have a number of taps. We have another lossless splitter. We go to taps, and then again we have a DNA, and then we go again to taps. So as you can see here, this is a complete network here, where we are distributing the signals, but the quality of this network is very good. So that means that all those customers that are connected to these ports can be connected on 4K QAM, even all the way up to 1.8 gigahertz. And what you also have in this case is that the power consumption of this network is roughly a third of the power consumption if we would build this with high power amps. And then the third thing, we have no filters in here. So this is what I mean with a transparent pipe. So all the signals that comes down here will be distributed to all the homes, and all the signals that come back from the homes will be distributed to this part here. So this is a way, this is an example how a DGA network can work. So now you can see that instead of having big amplifiers where we gain everything to reach a long cable, now we are using those small amplifiers. You can see roughly the size of a tap. We have the small amplifiers, and we boost that signal through the network. And what we try to do is we just keep the signal alive. We don't boost it too far to get in intermodulation, but we don't get it too low that we run into noise. We just keep the signal in the middle. That's the idea about DGA.
A couple of questions at this point, if that's all right. Just while you've got all this stuff on the wall behind you, probably the right time. First of all, just hopefully a quick and easy one. What's the payload associated with these amplifiers?
Payload, sorry.
Oh, Siri's talking to me at the same time. What's the payload associated for getting these kinds of levels with these amplifiers?
I'm sorry, James, I lose you in language. Payload, what do you mean with payload?
Let me get some confirmation. It was one of the questions that was raised. So let me go back and I'll get some further information. I'll ask you. Okay,
yeah, sorry. I don't know what you mean. Do you mean the signals, the quality
channel
of the
load
signals?
So I'll just add a further prompt.
Signal, yeah, the signal load what we use is what we can use, and what we also will demonstrate later on is that this runs from 54 megahertz down all the way up to 1.8 gigahertz up. So 1.8 gigahertz. So we have between 54 and 1.8 gigahertz down, and we have between 5 and 684 megahertz up. That is the signals that can run through this network.
Cool. And one just associates back to the reliability piece, which is around the power side of things. So power supplies are famously one of the points of value in a cable network. As we drive power requirements deeper into the network, any thoughts or kind of consideration around the power supplies having to feed all these?
Yeah, no, absolutely a very valid question. Yes, true. Power supplies is one of the weakest points in every active device, especially because they're in the field and they can get really warm, etc. And then the problem is that they get that warm is that the capacitors gets dry, you get ripple, they get broken, and you have to go over there to fix it. Same as with this. Only the big difference is that the power consumption in such a device is only about 6 watts. So that's why this power supply is a very simple, very down-to-earth power supply, and the unit don't get warm. And that's why we don't have that issue on that calculation on these capacitors. Absolutely true. We still the power supply of this unit sets the MTBF. That's so while we have bigger amplifiers, and with bigger amplifiers we talk about the hybrids, the power supplies, etc. When we look to the smaller amplifiers, the RF part is so reliable that the MTBF is set by the power supply. So yeah, it's a fair question, but because we don't have that stress inside the product, and we don't have that power consumption inside the product, the power supply is much simpler, and that's why it's much less sensitive for failures.
Cool. 2 more questions. I'm just going to read them straight out. So while we're here, how is the noise figure relation controlled due to the additional amplification stages in the network with the DGA solution?
Yeah, a very good question. The noise figure in these products is higher than the noise figures when you look to products like this. And the reason it's higher is because we build this with special couplers and instead of with diplex filters. And that's why you have your amplifier stage, you have the coupler in front of your amplifier stage, and the insertion loss of that coupler will add up to your noise figure. But because if you look to our levels here, we are talking about the input levels roughly around 20 dBmV, 25 dBmV input levels here. And then even when the noise figure is not 10, but let's say a noise figure of 20, a noise figure of 20 will generate a noise about 23 dB microvolt. So that 23 dB microvolt input noise that I have here inside my amplifier, and I have my signals around, let's say, 23 dBmV, then I have a distance between my signal and my noise of 60 dB. And the reason it's not so critical, because I have a higher input signal. Because we put them closer together, my input signal is higher, and that's why it's not important, that's so important for a noise figure, as when I have normal amplifiers, and I talk about input levels about maybe 4 or 5 dBmV. And that's why the noise figure is less important in DGA than it is in the traditional way of building a network.
Cool. And staying on the topic of noise for a second, if we can. With all the added noise coming back from all of the CPEs, what's the effect on the upstream signal quality?
The noise adds up with the number of amplifiers, 10 log the number of amplifiers. So in the situation here, where we have 1, 2, 3, 4, 5, 6, 6 amplifiers. I wish it was 10 because it's easier calculating. So 10 log 6 is around 7, 8 dB. So yes, the noise adds up about 7, 8 dB. Because that is, and downstream, of course, is divided and goes into different legs. And that's why it's not adding up as quickly as with downstream. Everything is bundled to one device. That one remote PHY device like we have here. And because we have all that amplifiers going down, all that signal coming up, then the noise adds up with 10 log that number of amplifiers. But if you have 10 amplifiers, the noise goes up with 10 dB. If you have 20 amplifiers, the noise goes up with 13 dB. And if you have 40 amplifiers, the noise goes up with 16 dB. So it's not that big difference. It is not that you say, oh, I have more amplifiers, now I have triple or whatsoever the noise. No, it adds up with 10 log the number of amplifiers. So the difference between 10 amplifiers and 20 amplifiers is only 3 dB from upstream.
Cool, thank you.
And there is one thing extra that I maybe should mention, is because we have more amplifiers in the network, and we also have gain in the upstream, as we can see in this approach. We also have amplifiers closer to the homes, because we now distribute the gain blocks. And therefore, if you want to go to maybe an ultra high split, where you go to 396 or even higher, because the amplifier is closer to the home, that modem don't have to transmit that extreme high level. And that higher level, that will absolutely cause problems for the modem device itself. the CPE device is under a lot of stress to be able to deliver a signal on 396 from the home to be able to reach a remote PHY device. But with distributed gain architecture, we have unity gain and we have amplifiers much deeper in the network. That small amplifier will help us, because now we have a 10 dB gain on 684, and that 10 dB gain help you that the modem don't have to deliver anymore. So overall, the performance of your upstream, you will see, is that the performance will be much better, because also here counts that you have intermodulation and noise. And although the noise maybe is 3 dB higher, your intermodulation is much lower, and therefore you will have a much higher quality on DGA on your upstream than when you had with traditional networks. Sorry for the sidestep, James.
That's cool, thank you.
Okay, great. If there are more questions about this way of building, otherwise we would like to show you the live amplifiers, and my colleague Diego will give you an example how we test this and how this is being used in the network. Okay, thank you. We move around the camera.
Welcome everybody, and thank you for waiting. My name is Diego Arroyo, CTO engineer for Technetix, and I'm here to present how a DGA architecture looks like. To do that, we built this setup over here, which consists on the CLGD, the DOCSIS generator, that we will connect to the setup over here after 160 meters of QR750 equivalent, the first amplifier, amplifier A, after 250 meters of coax equivalent to amplifier B, and after 250 meters of QR equivalent to the amplifier C. The idea for this setup is to prove what Jan was saying, that when we work in DGA, we have the intermodulation under control, and therefore the quality reduction is less. So what we are going to do is we are going to measure at this position over here in the generator, and we will see how the quality, the MER, is after 3 of these amplifiers. So I'm going to show you in my spectrum analyzer the channel loading that we are feeding this setup with. And so we have full load from 396 megahertz up to 1.8. And we are going to see now what's the quality at our starting position, in our generator. You can see here that our MER is around 44.3 dBs of quality. This is our starting position. So now I'm going to connect some cables. So I'm going to put this channel load to my setup, and I'm going to connect to the output of the last amplifier, and we will see how the quality changes. So if we go back again and refresh, we can see that the quality at 1.8 after 3 of these amplifiers has gone from 44 to 43.8. So it's less than half of the quality reduction after 3 of these amplifiers, proving the point that Jan was showing in the presentation before. Also, I would like to show you how this channel load looks at the output. Of course, after we connect this measurement equipment to the output of the third DNA amplifier, it has tilted behavior, so we can see that we have a tilted output over here. So that means that after, again, 250 meters of QR750, we will have a flat signal to be delivered in our customers. So we cover more than 800 meters of QR cable just with 3 of these amplifiers. So I hope you like this presentation. I'm going to pass back the torch to Jan and see you in some seconds. Please stay with us.
Okay, thanks Diego. This was the last moving around of the camera, so from now on it should be more stable, sorry. But we want to show you the DGA network, how this looks like on a wall, how it is really built with this 1.8 gigahertz steps, etc., and how we have the real situation of a network. And also via Diego, we want to show you the quality impact of, let's say, we have 3 of those amplifiers with around 800 meters of coax, and that the reduction on the quality was less than half a dB on MER. And that's what I mean with high quality. With 33.8 dB MER, of course, it's very easy to deliver a 4K QAM signal to the homes. The last part I want to cover is the financials. And I want to do this with 3 different networks. The first network I want to talk about is this high power network. We have seen this. So what we have here, we have a remote PHY, we have 4 output levels, we have 4 signals, we have the distribution amplifiers, we have the line with taps, line extenders, line with taps. This network can cover 480 homes passed. So we can connect 480 homes through this network. And we do this with high power amps. That is 35 watt power amplifiers to be able to distribute the signal to come to the next amplifier. The second network we want to talk about is what I showed you with our DBX. So here we have our normal DBX amplifiers. So it's half the power consumption as that high power amp. But because we know we cannot reach the next amplifier because we are 3 dB lower in signals, what we are doing, we add the DNA amplifier as a booster amplifier in the network. So now we have 44 plus 20, we now have 64 dB gain, and now we can easily reach the next amplifier. With the high power amps, I talk about 48 dB gain, and then we talk about that high power amp, we have 48, and now we have normal power, and now we talk about 64 dB gain. So that's the benefit we get about this approach. And then of course, the last one is DGA. So now you see, we only have small amplifiers. We have lossless taps and we have small amplifiers in the network. And I want to compare those 3 networks on the financials. And I want to look to everything involved to maintain a network for 10 years. So the total composite power, total cost of ownership, sorry. So if I look to those networks, and what is involved in total cost of ownership is, first of all, is the OpEx cost. OpEx cost is a combination of installation of an amplifier, power consumption of an amplifier. It is, if it gets broken, it needs to be repaired. If you want to change the split, you need to go to upgrade it, etc. So there are a number of things all combined that all falls into the OpEx cost. And if I then combine OpEx and CapEx, I have my total cost of ownership. So total cost of ownership is the total cost I need to invest in a network to build and maintain my network for, let's say, 10 years. So 10 years, what is the total cost I need to invest? And if I look to the high power amps, then this is how the high power amps total cost of ownership look like. The dark blue is the CapEx, the light blue is the OpEx. So we need to buy the amplifiers, we need to install the amplifiers, we need to power the amplifiers, need to upgrade them to go to a different split, etc. All of this cost is all involved inside this calculation. We did the same for the normal amplifiers here. With the booster amplifier, again, the CapEx we have here and the OpEx. And the same as what we have in DGA. And then here we have the CapEx and the OpEx. But you can see there is a big difference in the OpEx cost. Because DGA don't need to maintain, you don't need to go back to change something on filters, because now it becomes a software-defined network. Your labor time, your cost to invest in that network is much lower. And of course, the power consumption of this network is a third of the power consumption of the other networks. So that's a huge benefit. So if you would divide all this cost together and you divide this by the number of homes passed, and they all can feed 480 homes, then the cost of this network will be roughly around $58 per homes passed. If I go for the middle one, it's about 50. And if I go to the DGA, it's 37. So the cost to build, calculate, and maintain my network with taps, everything involved, is 58 versus 50 versus $37. And what I put extra in here is because I realized that DGA, you need to train the engineers. It's a different way of doing it. You need to calculate your tap values on a different way than you have a normal traditional network. So all of that cost is all involved in here. And that's why the OpEx cost in the beginning here is a little higher. But overall, you can see there is a huge benefit on your total cost of ownership of DGA versus the other networks. If I look now okay, this is what it will cost me to maintain and build a network. But how much can I earn with it? Because at the end, cable operators are selling data. They sell bits. They are buying components and maintaining a network, but they sell megabits. So how much megabit can I get through those networks? And if I look to that, this is the quality we can drive through a network with high power amps. And yes, we can do 4K QAM, maybe even up to 1.2 gigahertz. We don't know for real how high we can go, but we can say, but then we have to step back. We have to step back our quality because we cannot deliver that level and that quality anymore in the network because we lose too much in the coax. If I look to the normal amps, yes, we can deliver even up to 4K QAM, all the way up to 1.8 gigahertz, because now we have the booster to help us. So the stress in this amplifier disappears by that additional booster amplifier. And if I go for DGA, we can even go to a higher modulation scheme, but what we also win, we win the crossover area. We don't have a crossover area anymore because we have no filters. And that frequency is now also something we can use for data. So if you would add this up, then, and we use a K factor of about 1.3, then the signal that we can deliver here to the homes is about 7.8. The quality, the data we can deliver here to the homes is about 9 gigabit, and the quality of the data we can deliver here is around 11 gigabit. So you can see the network that costs the least can deliver the most data. So in a summarization, this is here, you can see the overview. That is 58 versus 50 versus 37 is the cost, the spending, but the earning, you can see this here, of course, with DGA, the financial side of it is that you can sell much more while it costs you much less.
Question around total cost of ownership just dropped in. I'll raise it now. What discount rate was used to calculate NPV of total cost of ownership?
Yeah, the NPV is a difficult one. I can do the NPV on the selling side or on the buying side, but it's difficult to calculate how much more money will it generate to go from 7.8 to 11 gigabit. But we know we can sell more data, but I'm not sure if you will generate 41% more income because you can sell more data. So it's a difficult calculation, but we would love to work with MSOs on this. We are very transparent with our calculations. We have an Excel sheet on this. And if they say this is the spending that we have, and if they can put how much money they can generate with this money, then we can do an NPV calculation.
Cool.
That was the only question, James?
For this point, yeah, I've got a couple. I'll ask on the kind of the wrap up bit if that's all right, but I'll let you continue this one.
Okay, that's great. So if I look to my conclusion side, so that will, I guess, will be the other questions then, James, is what we said in the conclusion side is that DGA, distributed gain architecture, can deliver more for less because you can have more capacity, you can have more quality and more reliability for less power consumption. That is what DGA can do. And if you combine DGA then with the DNA products like we have here, if you combine that, then suddenly we have a lot of more options because we take away the diplex filters and then we can, it fits all blocks. This can be used for extended spectrum DOCSIS when you want to go to 1.8 gigahertz, but it also works for full duplex DOCSIS, for FDD and to frequency split. And because we have no GAN band, again, we have more capacity because we don't lose that frequency somewhere in the middle. We now can glue the upstream and downstream together. In fact, one of the operators did a test with that. And they put the upstream up to 396 and they started the downstream on the higher frequency. On a higher frequency. And then they brought that down to see when was the impact on the upstream or on the downstream if they start to narrow that gap. and they went down all the way down to 0 megahertz gap. And then there was an impact of 0.1 dB on MER on the downstream. They could not see it on the upstream. So, but that's all down to the test equipment, because it's not our product that is causing that. It is simply because you have the upstream and downstream so close together that the test equipment didn't know exactly how to handle it. But that is to prove how that you can completely take away the guard band. If you have 1 megahertz difference, the impact was absolutely 0. So yes, so the DGA with the DNA products opens that opportunity for all that part. And therefore we believe it is not only that it is more for less, but with the DNA, it's double it, because it's much more flexible. And it gives you less labor, because after installation, you don't have to go back. It's the closest you can get of the last upgrade till you retire, because you install this, and now it becomes a software-defined network. Now you can control the splits, everything via software. So that's what your DGA can do. And therefore, as you can see in my calculations, DGA absolutely will give you a huge reduction on your total cost of ownership.
Cool.
This was my last slide. So yes, I believe we can help you. We have those products ready, and we can help you to make your networks 1.8 capable now. You don't have to wait. You can already do this via DGA now.
Awesome. A few questions, if I can just fast. Yeah. Conscious of time, we're a little bit over, but we've still got the majority of people on the call. So I'm going to just squeeze as many questions as I can in before kind of handing over to wrap up. Right. A lot of advantages on this slide. Everything looks really positive. A controversial question. Are there any disadvantages to DGA and kind of DNA?
Technically not. It's technically absolutely a much better solution. We cannot find a flaw where we say technically this is not a good idea. The only thing that we better say what is a disadvantage is that it's a different way of building a network, because you still have the same coax, but you have to think different, and therefore you have to train your staff to work with this part. But technically there is absolutely not a disadvantage of this part, and after the training you only will benefit from it.
Cool. Another question. Most networks use thermal or automatic gain control to track level at the pilot. Does this device support this requirement?
Yeah, we have 3 products. We showed you here on the wall, we showed you the DNA as a booster amplifier. We showed you the Lossless Splitter. That is a combination, is also a part of that family. And the third one in that family is we call it an intelligent DNA. And that DNA has indeed automatic gain control, automatic slope and level control. Yeah.
Cool. Cool. So one more for this point and I'll flip on. So we've been using coax for ages. Why haven't we thought of this earlier? Are there any drawbacks to the approach?
It's a good question. Good question. And I find it very difficult to answer. Why haven't we thought about this before? Probably because it was not needed. Because we had this, we went from 450 to 600 to 750 to 862 to 1 gig to 1.2, and we were always able to improve the product far enough to be able to go to the next step. We were always able of doing that, but now we have reached that limit. In fact, if you look to the performance of the amplifiers on the hybrids on the 1.8 gigahertz, simply are not as good as the hybrids we can buy at 1.2. So the performance is a little bit worse, and I know they are already much better than we could buy before, and they made a huge improvement on the performance already. The loss you additional will get to go from 1.2 to 1.8 in a trunk network is about 15 dB. And there is no way that we can close that gap anymore. So we have to start thinking different. And we said, okay, we have to go from going from working hard to working smart. And that's why we said this would be a better approach.
Awesome. Cool. One final question. Actually, interestingly, we've got a few, it could be operators coming in with a few real world scenarios and want to get your thoughts on an upgrade path kind of thing. So the final question before I go on to them too is, great technology, can this be adopted by other companies to make it more of a standard?
Yes, we're open for it. Technetix is open to share that information. We want to license that technology. We have developed on this technology for 5 years. It was not an easy fix. We had 5 years ago, we had the idea how to build this, and it has cost us 5 years to develop a product that could be very stable, gain in downstream, gain in the upstream on the same time, without turning this into an oscillator. And that took us 5 years. So yes, we want to protect our IPR, but we will license this technology if there are other companies that want to use this as well.
Cool. Right, so I'm going to throw some scenarios at you for upgrade paths, just 2 networks. These have been raised by kind of people on this call, so interested in your thoughts. So the first scenario, what suggestions or consideration would you have for an operator with a 2001 vintage 870 meg design system, which contains 875/625 P3 cable, 38 dB mini bridges, 31 dB line extenders, who are wanting to upgrade but set themselves up for DOCSIS 4. A lot there to process, but yeah.
Yeah. I need to think about it a little bit, James. But okay, I think we did now for around 10 operators in the world. We did all the calculations. How to go from a traditional network, as I was describing now, with amplifiers, line extenders, etc., to go to DGA. And so we most time went for worst case. So we took the most difficult area of that customer. And we said, okay, if you go for DGA, this is how it will look like. So many amplifiers you need. This is the quality you can deliver, etc. We do these calculations for our customers. And I'm sure that we also can have a solution for the customer that you are now referring to, James, because this is going to work. And if you have 860 megahertz network, you don't have to jump to 1.8. What this is, as you could see, the performance of this amplifier is anti-coax. That means that the higher the frequency, the higher the gain. So it doesn't mean that this only works for 1.8. This also works for 1.2. It also works for 1 gig, because then you also have gain. So you can already install this while your signals are maybe at 1 gig or 1.2. And in the future, you go to 1.8. It's fine. You don't have to touch your products. Everything is already there to be ready to go to 1.8 if you upgrade your remote via a CPE. You don't have to do this from day one. That's the beauty of this technology, because what we have, the loss of the coax is the same. It always goes down on the higher frequency. And the gain of this product is also the same. The higher the frequency, the gain goes up. And we have that compensated in that product. And that's why you have a flat line all the way down from 860 to 1 gig to 1.2 to 1.8. And it will work everywhere.
Cool. I'm going to chuck another technical question in. Sorry, I promised. Last 2, 1 scenario, 1 question, 1 just coming on the Q&A. How do you make level and slope alignment changes with the DNA?
Now we have 2 solutions for that. We have a passive solution, active solution. A passive solution is in fact that we the gain, the temperature control in the amplifier is absolutely stable. We don't drift over temperature in the amplifier. The coax, however, will. So the coax in front of it will drift based on the temperature differences. So what we do, we compensate that, because we can calculate, of course, is that if you have if you have, let's say, 20 dB gain, that is the same as Diego just said, 250 meters of QR750. So we can calculate how much per degrees Celsius, when it goes up or down, how much difference we need in gain. And that's why we can compensate in the product that the cable and the unit absolutely will be stable. That is a passive solution. So it is a pre-programmed, you can just plug that in and you have a flat line all over temperature. The other solution is that an active solution, and then we use a tuner and we measure 1 or 2 frequencies, and we will you install this, you press the button, it will measure it, and over time it will absolutely keep that line stable. So when temperature goes up and the loss of the coax goes up, he will give you more gain. And when the temperature goes down, he will give you less gain. So it will compensate it on a digital way via a tuner. There are the 2 solutions we are offering.
Awesome, thank you. Right, another operator scenario, this one less in depth. So what suggestions or considerations would you have for an operator with multiple DOCSIS 3 CMTSs that is currently considering upgrading to DOCSIS 3.1, but would also like a path to DOCSIS 4 in the future?
Yeah, no, DGA I think is a very good idea. And I absolutely agree that you don't have to jump from 3.0 to 4.0. You don't have to make that jump. You don't have to go further than you need at the moment. And that's also the beautiful thing about coax, because you can just make steps in the coax. You don't have to invest everything in the beginning. And like you have, for instance, with fiber, where you have to invest a lot of money before you generate money, can generate money. While in coax, you can just do this in step approaches. And then, of course, that's why the NPV calculation we discussed before for coax is much better than with fiber. But that's the same with this. So if you go from 3.0, you want to go to 4.0 in the future, yes, it's a great step to go to 3.1 first. But if you have to change your amplifiers and you have to change your taps to go to 1.2 gigahertz, why not going for DGA at the start? Because if you already put a 1.8 gig taps in there and the DGA in there, the DNA in there, so you have already a DGA network, you can easily go from 3.0 to 3.1. And in the future, you go from 3.1 to 4.0. And the only thing you have to worry about is your CPE device and your remote PHY device or your Mac device, because you don't have to worry about the network anymore because it's one big transparent pipe.
Awesome. Sounds great. Right, I'm going to have one more technical question, and I promise I'm going to hand over to wrap up. They're coming in thick and fast, which is great to see. So just on that kind of upgrade path route, when do you think demand will force most network operators to upgrade to 1.8 gig? Most have already upgraded to 1.2 gig.
Yeah, I'm not sure if you're. I find it a very difficult question. I think there are two things in play. There is a must-have because I cannot deliver enough bandwidth, or there is I want to compete with others, and that's why for marketing I need to make the next step. I think there is something people need to upgrade to compete with fiber, for instance, so they need to make a next step. But if it is absolutely needed, is a different path. Especially if you see that the CAGR in the network went down to from 50 to 40, that below 30%. But now due to this COVID situation, people are working from home. You see suddenly the data use is going up on the downstream and on the upstream. So yeah, that has boosted again that we need to put more data through the network. A year ago, nobody would imagine that would happen. So I find it very difficult to predict, James, when do I need to make that step? I think that differs absolutely per country. It depends on the competition of the country. If you have a lot of fiber companies, maybe you're under more pressure than when you don't have the fiber companies. So that will differ per country. But the beautiful thing is that if you look to the coax, the working area of a coax is maybe this wide. We are even using it for situations where we go to 4 gigahertz. So there's a huge bandwidth we can put on the coax. We are only using this part. So there's still a lot we can do in the future. We can still do a lot with that coax. And that's, of course, that is a huge asset to have. It's a wonderful asset to have, that coax cable.
Awesome. Thank you. That's all for questions. I'm going to say a massive thank you on behalf of everyone. You've fielded every question like a champion. I've had some great feedback as well to your answers, which is nice to see on the chat and stuff. So I will say thank you and wrap my bit up now. I'm going to hand in to Tony, I think, who may have a few words to finish things up.
Okay, thank you all. Thank you for joining. And if you have any questions, then please let us know.
Thank you.
Thanks, Jan. To take one of the person that's actually put something on here, solid answer, Jan is right. It doesn't get any better than that in the chat, really, does it? Thank you all very much, and especially to Jan. I appreciate the amount of work that's gone into preparing this presentation. It can't have been easy. You've actually been in depth on here, and I'm sure I speak for all of the attendees around the globe when I say we've learned a lot. I said at the start, this will be revolutionary. I hope I didn't disappoint. I don't think I did. My own opinion is this is revolutionary. This is an exciting time to be in the broadband sector, and we're at the very coalface of innovation. After all these years, it's still exciting. It still makes my head spin with all the possibilities that's going on. With my SCTE hat on, I have to say, We've seen more bandwidth change occur in the last year than we've seen in the last 50 years. The amount of bandwidth going through the network now is getting immense. Webinars like this, they're such a great learning resource, and it's only through discussions that we get more and more out of these. It gives us all a chance to take a step back and see how much this industry is pushing forward. Also, to take an educated guess, what's around the corner? Global pandemics and other disruptors aside, let's prepare for the future and see how much we're able to do. Coax is still impressing everyone. That's really important to our strengths as an industry. The relationships and the investment in those relationships, they're really what holds this all together. Being on some webinars recently where they said, thank you, anybody in the broadband industry, thank you. You have made it possible for the world to continue. I never thought that would ever be said about the industry I'm in. It was. This was from a leading MP in the UK. Impressive. The innovations are still coming. We're never going to get away from that. This is that step from Nokia to the iPhone. I'd like to thank Technetix for their involvement in this. I know a lot of work has gone into this webinar, being part of it, the high production value, and even putting a studio together. Come on, you've done a stellar job today. James, really well done. Terrific moderator. You didn't need to use control. I know how much you've put into this as well, so thank you very much. Thanks also to the team at the SCTE. There's a lot of hard work that goes on behind the scenes preparing for this. We really appreciate it. None of this would have been possible without the 124 attendees, the 180 that registered. Thank you all very much. There's going to be a little survey once we finish here. Please fill it out. I hope this has also given you some interest into the SCTE. We're still looking for members. We're still looking for people to join us as well and be able to join this great community where we can give this information around. Thanks again, everyone. Enjoy the rest of your day. Stay positive and test negative, please. Thank you all very much. Goodbye.